Let's move now to demand paging. I'm going to repeat some concepts because I think it's good for virtual memory to repeat some stuff so that you can hopefully digest it better. So we said that we could bring the entire process into memory when we want to start the process, but in practice, we can be more efficient if we just bring parts of it and then react when the process needs something that is not in memory. And this is, of course, beneficial because you generate less input-output, you need less memory, which means you can run more processes or allow more users to run more processes. Of course, you need to double check that if the process tries to access a page and actually that page is not loaded in any frame, then you take the actions needed to first put the page in a frame and then tell the process, okay, now you can access the page. You can go with different strategies here. You can go for something that is extremely lazy and then basically start the process without actually loading any page. As soon as the process asks for the very first address or the very first instruction, it will immediately generate an interrupt because you need to wake up the operating system and put at least the first page into the frame. So of course, it's not practical. You would start the process by putting actually some page because you already know that at least the initial ones will be needed. But from a theoretical perspective, you can even go with this lazy swap, but it can be used actually even in practice. So let's go through some basic concepts again. We have a pager, that is the one that brings the pages into the frames when it's needed. It's more complicated than just a paging system that takes all the pages and loads all of them in a frame before starting a process. In practice, you need to have extra functionality in the memory management unit. We will see, as always, you need to pay the costs either in time or in space. We will see that we pay in both space and time. Space when it comes to the page table and time when it comes to the time it actually takes to access a page if it is not there. Of course, if the page is already there, fine, then nothing needs to be done. When the page is not there, then we need to detect that and load the page before the process can actually access it. And of course, we want to do this dealing with this kind of problems at the operating system level. So when you write a program and you run a program, you don't write such a program so that it's compatible with a system that uses virtual memory. Actually, your laptop is using virtual memory, but when you write your program, you just ignore. So this is all things that are done by the operating system in collaboration with the hardware. So the first thing here we need is to know, is the page that I want to access in memory or not? To do this, we enrich the table, putting a bit in each entry, which is the valid invalid bit. If it's valid, it means then yes, then the page is in the frame. If it's invalid, it means the page is not loaded yet. So first I need to load the page, and then in this case is the operating system, and then you can access the page. Okay, so this information is actually used, this valid invalid bit, by the memory management unit when it does the translation to check if it's valid or not, if the page is in memory or not. So this is how it could look like, right? We have 8 pages here, but only 3 are in the physical memory with 3 frames, and those have the bit set to valid, while all the other bits, all the other entries are set to invalid. So page fault is what we call this event of trying to access a page and finding out that that page has not been loaded into a frame. When we say there has been a page fault, this is what we are talking about. Okay, when there is a page fault, the hardware generates an interrupt, the operating system wakes up, checks what's the cause of the page fault, and if it's about something that is not being loaded in memory, then it loads the missing page into a frame and tells the process that, okay, it can start again. The operating system needs to find a frame that is free. We will see that sometimes all the frames might be used, and the operating system also needs to take decisions when that happens. Then it swaps the page, only one page, into the frame. And this, of course, is a disk operation because you need to read. It updates the page table saying that now the reference is actually valid, and then it can restart the process that is trying to run. And this is basically what I just said, but you have the steps numbered here and the different actions. Have a look at the figure. As I said, you can go with a very lazy approach. You can call this, it's called pure demand paging, and start a process with no pages in memory. Okay. As soon as it starts requesting pages, you will get page faults, and you will keep loading pages as needed by the process. I mentioned this before many times. It's collaboration between operating system and hardware. And here you can already see the collaboration. We already discussed some of it. You need to enrich the page table. Okay, so actually what you store close to the CPU in some register to do the translation with this valid invalid bit. So the hardware is actually prepared to use valid invalid bits. You need the ability to restart an instruction. You try to run something, the operating system needs to wake up and replace or load the page into a frame. And then you need hardware support so that you can tell the process, try again to run the next instruction because the previous run was not successful because there was no page in a frame. And you can also rely on the hardware using the so-called swap space. Basically, you can take a portion of the disk and use it as if it was an extension of the memory to keep only pages there that you are swapping in and out when you are doing this, when you react to the fault tolerance, the page faults. It is costly, this I said. You need to generate a trap to the operating system, you need to save registers and process state. There will be a context switch, you need to wake up the operating system needs to understand why it is being waken up, so what is this interrupt about, find out that it's a page fault, double check if it's just a matter of loading a page into a frame or if it was a page fault because the process maybe was trying to access actually memory that does not belong to it. It needs to issue a read request from the disk and so on. Okay, so just really this sequence I already mentioned it. What I'm trying to say here is that there are a lot of operations. Okay, actually you can get an estimate of how bad it can get, right? So you have three major activities. You need to service the interrupt, you need to read the page, and then you need to restart the process. If you define P to be the page fault rate, 0 means there is no page fault. Basically, it means you load everything into memory, so it's paging without virtual memory. 1 is the laziest approach, means every time you need a page, you need to first load it because it's not in memory. Then you can compute the effective access time as 1 minus P times memory access plus P, the percentage, the portion of requests that are actually generating a page fault, times the page fault overhead, swap of the page out, so swapping of the page out if you actually need to free a frame, swapping of the page in if you need to, when you load the page that is missing.